All right, in this video, I'm going to continue with section 1.4 dealing with inverse trigonometric functions and their inverses, or just trigonometric functions and their inverses. This time, I'm just going to focus on inverse trig functions. All right, so we'll be focusing on this idea. We're going to find out what angle, and it could be any angle, theta, for example, such that the sine or the cosine of that angle will give us that numerical value, okay? So here the notion of inverse functions led from exponential functions to logarithmic functions. Now, in a previous section, we did talk about exponential functions and logarithmic functions. Those two functions are inverses of each other. The exponential function is the inverse of the logarithmic function and vice versa. So now we're going to use that idea of inverse functions with, this time, trigonometric functions. So here we're going to focus on first the inverse sine and cosine. So here our objective is to develop the inverse or the inverses of the sine and cosine in detail. The inverses of the other four trigonometric functions then follow in an analogous way. So far, we've already asked this question. If you're given an angle x, what would be the sine of x or the cosine of x? Now, this time, we're going to ask the question in an opposite way. Let's say we are given the number y. What is the angle called x such that the sine of x is equal to y? Or what will be the angle of x such that the cosine of x is equal to y? So those are just a couple of inverse questions. Now, what I have here is just an illustration of the graph of y is equal to the sine of x. So this is what the graph of that sine of x function looks like. All right. And it goes on and on forever in both negative and positive infinity. Now, let's say here, I want to find out what value of x where the sine of x is equal to 1/2. Well, if you look at it, since this sine function goes on forever, that means there are infinitely many values of x that will satisfy the fact that sine of x is equal to 1/2. Okay, they're infinitely many. Okay, now here's the problem with that sine function. It doesn't have unique answers because sine of x and cosine of x are not what we call one-to-one functions on their domains. Okay, if it goes on from negative infinity to infinity, that means the problem with that is it's not going to be one-to-one, and it's going to end up failing the horizontal line test because that horizontal line is going to cross that graph at infinitely many places in this case. So therefore, it's not one-to-one, and it would not have an inverse unless you restrict the domain. Okay, so like for the sine function, one good choice for that would be from negative pi over 2 to pi over 2. If we did that, then we pretty much would have a one-to-one function for the sine of x on that domain. And the same holds true, well, for the cosine of x, you have to use 0 to pi. Okay. Now, when we ask for an angle on the interval negative pi over 2 to pi over 2, where the sine of x is equal to 1/2, then you will only have one answer, and that will be pi over 6. And for the interval for 0 to pi, where the cosine of x is going to be equal to negative 1/2, then you'll only have one answer, and that will be 2 pi over 3. All right, now if you look on the next page, you'll see pretty much the graph of y equals sine of x. We'll start with that. If we were to restrict that domain of y equal to sine of x to negative pi halves to positive pi halves. Here's negative pi over 2 right here. Let's draw a vertical line there at pi halves, and another vertical line, well, negative pi halves, we drew a vertical line, but at positive pi over 2, we draw a vertical line there. You'll see on that window right there, if we restrict that window from negative pi halves to pi over 2, then the graph of this would have a one-to-one function based on that restriction. Okay, and I'm gonna put sheets of paper up here so you can see that it would have a one-to-one function. It would be one-to-one on that interval, and it would pass the horizontal line test. Okay, now let's look at the cosine of x, the graph of y is equal to cosine of x. If we were to restrict that domain, this time from 0 to pi. All right, so let's say here's 0 right here, which is of course the y-axis. So pi would be over here. I'm gonna draw a vertical line there. Within that window, I'll put pieces of paper there to cover the rest of this. So here's pi, and then there's 0. Between 0 and pi halves, it would be one-to-one, and it would pass the horizontal line test. Okay. So we would have an inverse function. All right, so now let's talk about this right here. Here we're going to define the inverse sine, or sometimes called the arc sine, and we denote that as y equals sine with a -1 as an exponent, and then x, that's actually read as the inverse sine of x. Or we can say y equal arc sine of x. Sometimes they write it like this. Some textbooks write it as arc sine of x, some write it as the inverse sine of x. They both mean the same thing, okay? So we're defining that such that y is an angle whose sine is x with the provision that y lies in the interval of negative pi halves to pi halves. That's the restriction. Also, we can define the inverse cosine or the arc sine. And that's also written as y equal inverse cosine of x or y equal arc sine of x. We can define it as that, such that y is an angle whose cosine is x with the provision that y lies in the interval from 0 to pi. And these are closed intervals, by the way, so that means that their endpoints are going to be included in that interval. Okay. All right, the formal definition is on the next page, where it says here y is equal to the inverse sine of x. That's going to be the value of y such that x does equal to sine of y, where y is a value between negative pi halves and positive pi over 2. And also y equal inverse cosine of x, that's going to be the value of y such that x will be equal to the cosine of y, where y is going to be a value between 0 and pi. And the domain for both sine, the inverse sine, and the inverse cosine are going to be this, from -1 to 1. X will be a value between -1 and 1. Because if you look at the graph of y equals sine of x, for example, it maxes out at 1 and it bottoms out at -1. Okay, because the value of the sine will go no higher than positive 1, and no lower than -1. The same holds true for the cosine of any angle. Okay, and I also have a couple of good charts that you can use here to assist you with inverse sine and inverse cosine. For the inverse sine, This is between negative pi halves and pi over 2. That's the restriction right here. Okay, and notice I do have the ordered pairs at each one of those. So let me kind of zoom out so you can see these right here. This is for the inverse sine of any angle. Okay, because you're going to be looking at pretty much the y value for this, because sine is always the y coordinate. And then you're going to match it up with that angle measure. And I'll only put this as in terms of pi, as you can see. Now, the next page is the inverse cosine. Notice the restriction for the inverse cosine, that's from 0 to pi. So I've only put this for 0 to pi. And also the cosine, of course, is your x coordinates. So you'll be looking for the x coordinate here and then match that up with the angle measure given in terms of pi. Okay. So now we're going to do some examples of just this using those two unit circles that I gave you. Now, by the way, if you want to, you can pause the video and try to copy this down if you like for the sine and also for the, well, inverse sine I just showed you, and also for the inverse cosine. And now let's go into some examples here, like example 8 in your handout. It says here, we want to find the exact value in radians of the expression, the inverse sine of negative 1/2. Inverse sine of negative 1/2. And what that really means here is this. We're trying to find some angle, which I'm going to call theta, such that the sine of theta must equal to negative 1/2. Okay, and this is where we use our unit circle right here that I have here. So here, keep in mind that the sine is going to be the y coordinate. So I need to find the y coordinate that contains negative 1/2. And in this case, here's negative 1/2 here. That's the y coordinate. That represents the sine of the angle equaling negative 1/2. Now I need to match this up with the angle measure that corresponds to where the sine of that angle will give me this 1/2. And it has to be, in this case, negative pi over 6. And the reason why we're using negative pi over 6 instead of the other angle, because of the restriction for the inverse sine. Has to be between negative pi over 2 and pi over 2. Okay, because the negative angles go in the clockwise direction, as you can see. The positive angles go in a counterclockwise direction. So for negative 1/2, that angle measure would be negative pi over 6. So that means that angle here will be negative pi 6. So here, negative pi 6 would be the angle where the sine of theta will be equal to negative 1/2. And negative pi over 6 represents the inverse sine of negative 1/2. Okay. All right, part B. Without using a calculator, evaluate, if possible, the following expression, the inverse sine of 0. And what that means here is this. We need to find what angle where the sine of theta would give us 0. So we're looking for the angle theta where sine of theta would be equal to 0 using this chart. So in this case here, sine of theta, we look at the y coordinate because the y is always going to be sine. That's 0. which means here the angle measured for that will have to be, of course, 0. So theta is 0. And the inverse sine of 0 would give us 0 because sine of 0 is 0. Okay, now let's look at part C. In this case here, we want to evaluate the cosine of the inverse cosine of negative 0.5. Okay, so now let's look inside, let's focus on what's inside the parentheses here. The inverse cosine of negative 0.5. I'm going to label that as theta. So that means that the inverse cosine of negative 0.5 is equal to theta. Now, what that really means here is this. I need to find the angle theta such that cosine of theta is equal to negative 0.5. Now, of course, negative 0.5, if I was to write that as a fraction, that would be negative 1/2. So I need the angle theta where cosine of theta gives me negative 1/2. All right, so let me pull out the unit circle that has the inverse cosine. And that's this right here. Now for the inverse cosine, cosine is always going to be your x coordinate on the unit circle. So I need to find the x coordinate that has negative 1/2, or the ordered pair that has negative 1/2 as the x coordinate, because x is always equal to the cosine of that angle. And here it is right here, negative 1/2. The angle that corresponds to that will have to be 2 pi over 3. Okay, so angle theta would be 2 pi over 3. Okay, but I'm not done with that problem yet, because notice I have the cosine on the outside. So I have the cosine of theta, which we found out to be 2/3 pi, or 2 pi over 3. Now, we can use the unit circle if we want to and find the cosine of 2 pi over 3. Now I'm using this regular unit circle here as well. Let's find 2 pi over 3, which is right here. The x coordinate represents the cosine, so the x coordinate for 2 pi over 3 is, of course, negative 1/2. So that means that the cosine of 2 pi over 3 will end up being negative 1/2. So the final answer for that would be this. The cosine of the inverse cosine of negative 0.5 ends up to be negative 1/2. Okay. All right, so that's how we simplify that problem. All right, now here's part D. Again, without using the calculator, evaluate if possible the following expression. Here we got the inverse sine of the sine of 5 pi fourths. Okay, so here, this part right here, I'm going to do up to the side and evaluate the sine of 5 pi fourths. Okay. Now I'm going to use the regular unit circle to find 5 pi over 4. Let's see, 5 pi over 4 would be right here. And the sine, of course, is whatever the y coordinate is for that point at 5 pi over 4. So that y coordinate here will have to be negative square root of 2 over 2. Okay, so the sine of 5 pi fourths would be negative square root of 2 over 2. Okay, so from here, I'm going to do the inverse sine, bring that down. And the sine of 5 pi fourths came out to be negative square root of 2 over 2. Now, the next thing I need to do here is this. I need to find out what angle for theta, so that the sine of 5 pi, the sine of pi will be equal to negative square root of 2 over 2. Need to find out what angle theta will be so that the sine of theta will be negative square root of 2 over 2. Okay, so here I'm going to go to this table, this unit circle for the inverse sine, and I'm going to find negative square root of 2 over 2. And the sine is that y coordinate where I have negative square root of 2 over 2, which is right here. And the angle that is associated with negative square root of 2 over 2 for the y coordinate will have to be negative pi over 4. So the angle that I'm looking for will have to be negative pi over 4. That represents the inverse sine of the sine of 5 pi fourths. Okay. All right, next we'll look at finding the inverse sine of negative square root of 2 over 2. And this is going to be in radians, by the way. Okay. And the key word they tell you, you need to give your answer in radians, nothing else. So that means here, I need to determine sine of what angle theta gives me negative square root of 2 over 2. All right, so I'm going to use the unit circle for the inverse sine, which is this. And I'm going to find negative square root of 2 as a y coordinate, okay? Because keep in mind, sine is always going to be the y coordinate on the unit circle, which is right here. And the angle that is associated with it is going to be negative pi over 4. So that means that the inverse sine of negative square root of 2 over 2 will end up being negative pi over 4. Okay, now part F is finding the exact value, again, in radians of the expression. Now, this is the arc sine of negative 1/2. And another way of writing that would be something like this. That's the same as saying the inverse sine of negative 1/2. The inverse sine of negative 1/2. And what that means here is this. I want to know what angle theta will be so that the sine of theta equals negative 1/2. And again, we're going to be using the unit circle that contains inverse sine. And the y coordinate is what sine of theta will be equal to. So let's find negative 1/2 as a y coordinate, which is right here. So for negative 1/2, the corresponding angle for that would be, in this case, negative pi over 6. So here theta would be negative pi over 6. Okay. And you're probably thinking, where am I getting negative pi 6, negative pi 4, negative pi 4, negative pi 6, and negative pi over 2? Well, here's 0 right here, and that's pi over 6. If I go in this clockwise direction, it's going to be negative. So this angle will have to be negative pi over 6. And of course, if you look here, these are opposites here. Pi 6, negative pi 6. Then the next one, pi 4, negative pi 4. And then up here, pi over 3. Pi over 3, negative pi over 3. And I need to change that to negative pi over 3, by the way. because these two are inverses, pi 3 negative pi over 3, and then pi halves negative pi halves. And if you look at the ordered pairs here, okay, we're dealing with the first and the fourth quadrant. In the first quadrant, both x and y are positive. In the fourth quadrant, just the x is positive and the y is negative. They have the same values. Here's positive, the y is negative. This one's positive, that one's negative. This one's positive, that one's negative. This is positive and that's negative, okay? Okay, now let's move on to part G. Inverse sine of the square root of 2 over 2. Inverse sine of the square root of 2 over 2. And what that means here is this. I need to find out what the angle theta will be so that the sine of theta will be square root of 2 over 2. So I'm trying to find out what theta is going to be. All right, so let's go back to that inverse sine. And in this case here, we're looking for a square root of 2 over 2. Just the y coordinate, because sine is always the y coordinate again. So here's square root of 2 there. And the corresponding angle measure will have to be pi over 4. So for the inverse sine of the square root of 2 over 2, that will be pi over 4. Okay. Now let's look at H. Here we're going to find the value of alpha so that the sine of alpha is equal to negative 0.2833. Now here the restriction is that alpha is going to be an angle between negative 90 degrees and positive 90 degrees. So our answer has to be in degrees here because of these restrictions here, not radians, has to be in degrees. So if you're going to use your graphing calculator for this, what you're going to have to do here is this, because you want this in degrees. Make sure you do this. Press the mode key, which is at the top of the calculator next to the second key. Press mode. Now notice that radian is highlighted. You want that in degree measure. So what you're going to have to do here is use your down arrow key to go down to where radian is. Use your right arrow key to put that cursor on top of the word degree, and then press enter. Okay? Because you want your answers in terms of degrees here. And then you can hit the clear key to get out of it. And then here's what we're going to do. We're going to do this. Notice you have your sine, cosine, and tangent buttons here. Right above those is inverse sine, inverse cosine, inverse tangent. To access those, you must press the second key first. So we're going to press the second key. And we're dealing with sine, so we press the sine key for the inverse sine, because your screen should have the sign with the -1 for inverse sine. And then we can type in that value. In this case, we're going to type in negative 0.2833. Now make sure that you use the negative key at the very bottom of the calculator and not the minus sign. Do not get those confused. Close parentheses and then press enter. And this will be your angle measure between negative 90 degrees and positive 90 degrees. Let's say I want to round it out to 1 decimal place. In this case, it will be approximately negative 16.5 degrees. So our angle alpha will be negative 16.5 degrees. Okay. All right, now let's look at I. Here I want to find the exact value in radians of the expression, the inverse cosine of 0. And we're going to use our graph to help us picture that problem. So that means the inverse cosine of 0 means this. I want to find out what the angle theta is so that the cosine of theta is equal to 0. Now this time I'm going to be using the unit circle for inverse cosine. Now keep in mind cosine is always your x-coordinate. So I want the x-coordinate for that contains 0. I want the point where 0 is my x-coordinate, which is right here. And the angle that is associated with that will have to be pi over 2. So in this case here, pi over 2 is what the inverse cosine of 0 will be, because the cosine of pi over 2 is 0, if you think about it. Okay. All right, let's look at the next example, where we have the arc cosine of negative square root of 2 over 2. Arc cosine of negative square root of 2 over 2. What that means here is we can write that as the inverse cosine of negative square root of 2 over 2. And what that means here is this. I need to find out what angle will that be so that the cosine of theta would be negative square root of 2 over 2. Okay, so now we're going to use that unit circle that contains the inverse cosine. And we're going to look for negative square root of 2 over 2 as our x-coordinate. Well, by looking at it is right here, negative square root of 2 over 2. That is the x-coordinate for the cosine. The corresponding angle for that will have to be 3 pi over 4. So the theta will have to be 3 pi over 4. And that would be the arc cosine of negative square root of 2 over 2. All right. All right, part K. Here's another one of these. In degrees, here it is. Read carefully. In degrees, you want to find the exact value of this expression. That's the cosine, the inverse cosine of negative 1/2. And what that means there is, I want to find out the angle theta so that the cosine of theta is negative 1/2. So going here to the unit circle for inverse cosine, I want the x-coordinate for 1/2. The x-coordinate for actually negative 1/2. Need the x-coordinate for negative 1/2, which is right here. Because this point has the x-coordinate of negative 1/2. The corresponding angle for that will have to be 2 pi over 3. Okay. But it does say we need the exact value in degrees. This is in radians. Now, if you recall in the first video, section 1.4, we can convert from radian measure to degree measure. And that is multiplying it by 180 degrees over pi radians. And what's going to happen here is this. The pi's divide out. And if I divide 3 into 180, that's going to go 60 times. And then 2 times 60 degrees would be 120 degrees. So in degree measure, the inverse cosine of negative 1/2 would be 120 degrees. So here you have to pay close attention on what they're asking for, either in radians or in degrees. So if you use that unit circle for the inverse sine with the inverse cosine, the angles that I give you are in radians. You can convert that to degrees by multiplying by 180 over pi to get this. Okay, part L. You want to find the value of alpha, where alpha is between 0 and 180 degrees, so that the cosine of alpha will be equal to 0.5182. So here we have to use our graphing calculator to do this problem. In this case here, I'm going to press the mode key to make sure that degree is highlighted. The word degree is highlighted because I want my answer in terms of degrees. Okay. And then I'll clear this. And then for the inverse cosine, which is what we want, okay, we press second and the cosine button for inverse cosine, and then type in 0.5182. Close parentheses, hit enter. So here is our answer in degrees. Now to one decimal place, this will be approximately 58.8 degrees. So that means alpha is 58.8 degrees. Okay. Now make sure that the calculator is in degree mode before you attempt to do these types of answers where they want them in degrees. Okay, now let's look at example 9. And there are 3 problems that I have in this video where you're going to be using a right triangle to write each expression as an algebraic expression. You know, right? Use each right triangle. You're going to create a right triangle and you're going to write each expression as an algebraic expression. Like in part A, you got the cosine of the inverse sine of 10x. Cosine of the inverse sine of 10x. So we're going to come up with the algebraic expression for that. All right, first thing I need to do here is focus on this inside the parentheses, the inverse sine of 10x. And I'm going to let theta, some angle, be that. So here the inverse sine of 10x, that's going to be equal to theta. All right. What that means here is this. I need to find some angle theta so that the sine of theta will be equal to 10x. Now, since I'm going to be using a right triangle, I'm going to write this as a fraction. I'm going to write 10x as 10x over 1. And then we'll go ahead and draw the right triangle for this. Okay, so here's my right triangle. And this is going to be angle theta right here. This is the right triangle. Now, according to one of our trigonometric relationships, the sine of theta is always going to be the opposite side over the hypotenuse. Sine of theta is always going to be the opposite side over the hypotenuse. And somewhere in the handout for section 1.4 is this. Sine theta is opposite over the hypotenuse. So if this is theta, the opposite side is right here. That has to be 10x. The denominator is the hypotenuse. The hypotenuse is the longest side of that right triangle. That's going to be labeled as 1. And A is what I'm trying to find, the length of that side. To do this, I need to use what they call the Pythagorean Theorem. And the Pythagorean Theorem states this: a squared plus b squared is equal to c squared. In other words, the square of the hypotenuse will always be equal to the sum of the squares of the two legs in that right triangle. A squared plus b squared is equal to c squared. And now we just do some substitution here. A is what I'm trying to find, so I'm going to bring down the a squared plus b, that's this length of that leg, that's 10x, so it'll be 10x and that's squared, equals to c, which is your hypotenuse. That's going to be 1. So this is b and that's c, by the way. And that 1 is going to be squared. All right, so now let's simplify this. Bring down the a squared. If you square 10x, that means 10 squared will be 10 times 10 or 100. Your x will be squared equals 1 squared is 1. Now we need to solve for a. I need to get the a squared by itself, so I need to subtract 100x squared on both sides. So that means a squared is equal to 1 minus 100x squared. And then to solve for a, it's squared, so the opposite of squaring something would be to take the square root on both sides of that equation. So that means a will be by itself, and that's going to be equal to the square root of 1 minus 100x squared. And I'm not going to worry about the plus or minus symbol. Okay. So a is equal to 1 minus 100x squared. Now for this, I can find the cosine of theta. Since I'm letting the inverse sine of 10x be theta, that means I'm going to have cosine of theta. I can find out what cosine of theta is from this triangle. If you recall, the cosine of theta is this. Cosine of theta is going to be the adjacent side over the hypotenuse. Adjacent over the hypotenuse. So here, the adjacent side of angle theta is this, the square root of 100 minus x squared. 1 minus 100x squared, square root of 100 minus x squared. That's divided by the hypotenuse, which is 1. Okay, so cosine of theta would just simply be the square root of 1 minus 100x squared. And then if I replace that theta with what this is equal to, the inverse sine of 10x, I will have the final answer, which would be cosine of the inverse sine of 10x is equal to the square root of 1 minus 100x squared. Okay. So that's how we use the concept of that right triangle to come up with an algebraic expression for the cosine of the inverse sine of 10x. Okay. Here's another example. This is part B on the next page, which is this. Let's say I want to find the cosine of the inverse sine of 8 over x. Okay, here's how we start that problem. Take what's on the inside of the parentheses, which is the inverse sine of 8 over x. Set that to be equal to theta. So here, inverse sine of 8 divided by x is equal to theta. So now we're going to have to find out what that angle theta is, so that sine of theta is equal to 8 over x. And let's create a triangle, a right triangle to be exact. with this relationship. Okay, there's theta, that's the right angle. Again, the sine is the opposite side of angle theta divided by its hypotenuse. So here, if this is angle theta, this is our opposite side of angle theta. That's going to be 8. The hypotenuse is x. Keep in mind, the hypotenuse is the longest side and it's always opposite the right angle. And again, a is what I'm trying to find. So here I need to use the Pythagorean Theorem, which is, of course, a squared plus b squared is equal to c squared. And a is what I'm trying to find, so I'll bring down the a squared plus b, that's this leg, that's 8, it will be squared, equals to c, which is your hypotenuse, that's x, that too will be squared. All right, now simplifying this, this will be a squared plus 8 and you square it will be 64. That's equal to x squared. Now here we're solving for a. Keep that in mind. We're looking for the length of a. So we need to get a squared by itself. So we need to subtract 64 on both sides of that equation. So I'm going to do minus 64 and then minus 64 on both sides. So that means a squared will be equal to x squared minus 64. And then to get a by itself, we're squaring it. So I need to take its square root on both sides of that equation. So that means a will be by itself, and that's equal to the square root of x squared minus 64. So a is the square root of x squared minus 64. Now, the outside trig function is cosine. So we're finding the cosine of theta. And the cosine of theta is always the adjacent side over the hypotenuse. Adjacent over the hypotenuse. So the adjacent side of angle theta will be the square root of x squared minus 64 divided by the hypotenuse, which is x. And finally, we'll go ahead and substitute theta with the inverse sine of 8 over x. So this, our final answer will be cosine of the inverse sine of 8 over x would be equal to the square root of x squared minus 64 all over x. Okay. So that's how we solve that problem. And finally, part C. We have the sine of the inverse secant of the square root of x squared plus 100 divided by 10. And we want an algebraic expression for that. All right, so I'm going to take all of this that's inside the parentheses, set that equal to theta. And all of that I'm talking about would be the inverse secant of the square root of x squared plus 100 divided by 10. So I'm letting theta equal to the inverse secant of the square root of x squared plus 100 divided by x. Now, I need to find out what the angle theta is so that the secant of theta will be equal to this, the square root of x squared plus 100 divided by x. And now we're going to use we're going to create a right triangle from this. All right, so here's theta. Now, let's think about the relationship for the secant of theta from this right triangle. Secant of theta is the hypotenuse over the adjacent side. Okay, keep in mind, secant is the reciprocal of the cosine of theta. So secant of theta is the hypotenuse of the adjacent side, since the cosine is the adjacent side over the hypotenuse. So the hypotenuse is our numerator this time. That's the square root of x squared plus 100. The adjacent side is our denominator, that's the x. Where did I get x from? That should be 10. I'm sorry. It should be 10 here. That's 10 here. So that means that 10 is our adjacent side, opposite over the adjacent side. And b is what we're trying to find, the length of this leg here. All right, so let's use the Pythagorean Theorem on this one. And that would be, of course, the a squared plus b squared is equal to c squared. All right, so a is this length going across here, that's 10. So that'll be 10 squared plus b is what we're trying to find, b squared, equal to c squared. Well, c is the hypotenuse, the square root of x squared plus 100. That whole thing will be squared. And then we simplify. 10 squared, or 10 times 10, will be 100, plus b squared is what we're trying to find. Now, if you take the square root of something and you square it, it's going to be what's underneath the radical. So the square root of x squared plus 100, we turn around and square it, is going to end up being x squared plus 100. Because the square root and the square of something wipes out the radical. You'll be left with what's underneath it. All right, so now we need to get b by itself, because we're finding out this length, which I labeled as b. So that means I need to subtract 100 on both sides of this equation to get b squared by itself. So now you got b squared is equal to just x squared, because plus 100 and minus 100, that's gone on the right side and on the left side. So now let's get b by itself. We're squaring it, so I need to take the square root on both sides. So the square root of b squared is b. Square root of x squared is just plain x. So that means b must be equal to x. Now, the outside trig function is the sine. So I'm going to find out what the sine of theta is from this right triangle. The sine of theta is always the opposite side over the hypotenuse. Opposite over the hypotenuse. So the opposite side of opposite side of angle theta here will be x. The hypotenuse is the square root of x squared plus 100. And I will leave it like this. And then I replace my theta with the inverse secant of the square root of x squared plus 100 all over 10. So the final answer there will be the inverse sine of, the sine of the inverse secant of the square root of x squared plus 100 divided by 10. That will be equal to that expression, x divided by the square root of x squared plus 100. And again, don't worry about rationalizing the denominator by multiplying the numerator and the denominator by the x squared, square root of x squared plus 100. Okay, we can just leave it as this. Okay. Okay, so that concludes part 4 of section 1.4, dealing with just trigonometric functions and their inverses. So that includes, this right here includes the entire section altogether. That was the last of the 4-part section. All right, feel free to email me or contact me if you have any questions on anything that's presented in this video or in the homework on my math lab.